Yes, can you hear me?
Yes, thank you. Go ahead.
Perfect. Thank you. Sorry, I have just to. Okay. Yes. Thank you, Fumia, and everyone who's organized this workshop. It's really exciting so far. And I try to keep it short. So my view on embodied intelligence comes basically from being a roboticist. So like Jamie, we are very interested in understanding how we can build better bodies for our robots. And something that I would like to propose today is a little bit for stimulation of the discussion, is something that we should see embodied intelligence as something that is much more dynamical than what's currently done. And I think with the summary that you gave for me, I think some people have already pointed it out. So I think it's good to see that I'm not alone with that. And there might be some overlap there, and I will point out to that along in the presentation. So what do I mean by having a more dynamical approach within robotics and embodied intelligence? Well, in our group, what we are looking at is, and I borrow here the figure from Rolf Pfeiffer, where you have the body which sits in the middle between the brain / controller and the environment. And it's negotiating information and energy between these. So it's this kind of partner in the middle who is talking to both sides, so to say. And we're looking at 2 points in our group. So one side is we're looking at how can we build a good body, a good morphology for a robot in order to improve the interaction with the environment. So this could be to increase energy efficiency in locomotion, but also it could be to build better sensing morphologies, for example. And the second part of our research question is on the other side, where you talk about how can we build bodies and morphologies that actually help us to facilitate the learning and the control problem, to accelerate learning, to make it easy to control the body of the robot. And in both aspects, it turns out that seeing the body as something that is not just simply a static morphology, but much more dynamic and changeable, helps us to come up with more kind of approaches to explore and exploit embodied intelligence in robotics. So particularly 2 points I would like to point out. One is, I think the morphology is best described with the help of analog dynamical systems with differential equations, because the body itself interacting in a real world environment is better described as such than with digital means or with Turing machine approaches and so on. And the second part is, I also think embodiment should not just be a static solution, a morphology that solves a particular solution, but rather we should build the bodies of robots that can actually provide the emergence of solutions. It's in a solution space, and mostly through the interaction with the environment, we can get to this kind of solutions. Now, let me talk a little bit more about the first part. Everything is a dynamical system. What do I mean by that? Well, in the more abstract sense, like in morphological computation, any kind of computation that should be carried out in the body, I think is best described with analog computational models. So I would like to suggest to move a little bit away from Turing machine kind of approaches, digital kind of approaches, logic gates, because I think it's a more natural way to describe a physical body interacting with another physical body with the help of differential equations. Now, one way to capture that is, and it's not the only way, but one way is physical reservoir computing. And it's great to see that in recent years, it has gained a lot of momentum. And again, I want to point out the body here depicted as some kind of network of mass spring tempo system doesn't have to be mechanically, right? It could be chemical interaction, electrical, electromechanical, or a mixture of all of them. So as long as we have this kind of way to describe complex dynamical systems, we can carry out computations because we can use it as a resource. Now, computation is very abstract. More concrete is control in robotics. Obviously, control in control theory is a dynamical systems by definition. And before we had means to implement digital controllers, control was implemented as mechanical systems, like the steam governor. I think Metin showed it in his talk as well, which helps us basically to understand that we can shape the landscape of the attractor landscape of some kind of controller with the help of the morphology. So we can say we can design the robot in such a way that it stabilizes. And especially in soft robotics, where we have passive dampening dynamics, we get a lot of self-stabilizing systems. So you can define controllers through the morphology. And furthermore, if you have a complex enough morphology, you can have multiple controllers implemented in the same morphology. And the really cool part about that is switching between these two is very easy, right? You just get to have over this hump, which means the control, the switch can be quite imprecise as long as you're pushing it into the right direction and it's big enough to get over this little hill. And on the other side, the new controller with this attraction space around it actually pulls it in and then stabilizes it. So we can take a lot of advantage of soft mechanical structures in robots if you understand it as a dynamical system. Now, sensing is another aspect which I think should be seen as a more dynamical approach as well, not just measuring a value and then that's provided for the computer. So the body sits in between the brain and the environment. So we should actually see them as a dynamic filter. So there should be a memory in a mechanical structure or the chemical structure or whatever means you use for implementing such a sensing device. And even more so, you can adapt the morphology in order to shift the focus of this filter to different kind of frequency bands, for example. And this is something which hasn't been researched a lot. The only thing that I'm aware of is, for example, Trish is doing some work in Imperial, which is really interesting, where they adapt the stiffness in order to improve the extraction of information by interacting with the environment. And finally, also behaviors as a more general principle can be described nicely as this kind of attractor landscapes. So this could be also not just a equilibrium point, but actually a limit cycle, and you can switch between those. Now, this also means if you want to change the behavior, we also can change the morphology, right? And we can do it in a very smooth way, in a very dynamic way. So we can change the morphology and then end up with a new behavior B, which is different from A, and they don't exist at the same time, right? You just change the morphology. And if you do it very clever, you don't have to change a lot of parameters. For example, there's some work that has been done by Francesco Corrucci. It was really nice, where I looked at an octopus robot where they received all the same control signal. It's a standard function, and then the body is translating this input into a certain behavior. For example, the robot was walking on the ground of the sea. And then he was able to find just one parameter to switch over without changing the controller. And then suddenly a new behavior emerged. So it was swimming with the same control signal. It's just the body shifted and then it's doing something different. Now, what about the other part? Embodiment as a solution space. Well, the body is not just something that is fixed, in my opinion, but actually, as we can see in nature, it's a lifelong learning experience and it changes. And one of the key elements of this change is interaction. So if you have a body, some kind of soft passive tissue with some smart material or maybe a hybrid approach, and then you expose it to a certain environment, there's an interaction going on. For example, a force, a chemical stimulation, whatever it is, but it's going to be locally. And then locally, this material reacts to the stimulation and changes the morphology locally. And if you have a more complex body, can actually do a set of different stimuli and therefore do a set of different morphological changes. Now, you can use that for designing robots, for example. So this is a work by Catherine Walker, where she looked at a voxel-based robot. There is this kind of contraction, heart muscle in the middle, and she wanted to optimize it for locomotion. Now, she optimized not the morphology nor the controller, but she optimized rules that were able to make an interpretation of the feedback of the forces from the environment and chain into changes of the morphology, specifically changes in the stiffness. And if the stiffness was below a certain threshold, the robot removed this voxel. So through these rules and interaction with the environment, the robot came up with a solution which was locomoting very, very nicely. Now, a really cool part is this kind of rule is not connected particularly to this landscape. You can throw the same robot with the same rules into a different environment. You get different kind of feedback, right? And with the same rules, the different feedback will then evolve into different kind of morphologies, and you get a different optimal robot. And then another aspect of that is learning. Learning is very much connected with the morphology in real systems, but not so much in robotics. So there's some work, for example, that has been done by Josh Bongard. We did something similar, but with a robot that should grow from a tadpole into a frog robot. And the idea is it's very hard to find control parameters for a big robot as a frog, but very easy for a tadpole. So you find a solution and then you slightly change the morphology, which means the solution for this new kind of morphology is very close to the previous experience. So you can slightly adapt it. And then you adapt the morphology and then a policy again. So you're beckoning along with this growth process, the actual optimization process, and then you end up with something which is much more robust. So you can see at the end, everything goes into this direction, at least in my mind, into growing robot. So sooner or later, we have to implement more sophisticated ways that can actually implement changes from coming from stimulation from the environment into morphological changes. And I think that is very particularly important for small scale robots, as Metin pointed out the other day. And I think this will be a crucial part in order to get embodied intelligence a little bit more dynamic in the next step that we have to take in the context of robotics. So that's all from my side. Thank you.
All right, thank you, Helmut. It's perfect 10 minutes. So we come back to this, lots of interesting discussion points, I suppose. So we get back to you later.